This video is going to walk you through the purify case. So in this case, we're making some product or some chemical process, and one of our one of our staff members had the idea of adding an additional step to the process where we add some purifier. And the thought behind this is that by adding this purifier, we'll increase the yield from the process. So we want to try this out and see if this is indeed the case. If it is, then we'll start adding purifier so that we can increase the yield. Otherwise, we won't. So let's go take a look at the data. And if you just type purify, you can get this data set from Blackboard. You'll see what we did. We ran some tests where we varied the amount of purifier. So that's X. We created a batch of this material and measured the yield, which is Y. So this first run amounted to us not putting any purifier in. So this represents business as usual. So without any purifier, the yield was 13.39. We then added 1 unit of purifier, and you'll see the yield actually went down a little bit to 11.86. We then tried adding 2 units of purifier, and it went up to about 28. And we took this all the way out to about 10. And you'll see that the yield was about 21. So the question is whether adding this purifier improves the yield. So do we get more product after adding this purifier? Let's do something that I told you not to do in class, which is go fit a regression model without looking at the data. So let's just go jump in and fit a regression model. So fit is going to be an LM. Let's regress Y and X, and we're going to use the purify data set. Now if I do a summary on fit, what you'll see is that we have an insignificant coefficient for X. So what does this mean? What this means is if I wanted to test the null hypothesis that the slope was non-zero. So the slope is for a unit change in purifier, what happens to my Y? Well, you'll see that I cannot reject the null hypothesis that this coefficient is equal to 0. And therefore I can't conclude that X has a linear relationship with the dependent variable, with the yield. You'll notice that the overall test of significance given down here at the bottom is exactly equal to that at t-test, and leads us to the same conclusion that this linear model isn't doing anything for us. Well, this gives us a good opportunity to use our residual plots. So if we plot the fit, what you're going to notice is that the residual plot looks very bad. So on the one side we have points that are systematically below the line, then we have points that are systematically above, and then we have points that are systematically below the line again. So that's an indication that this model isn't very good. So we really need to go back and fit a better model. So let's go do something that we should have done in the first place, which is to look at our data. So if we plot the object, we'll get a simple scatter plot. And what we see is that it appears we have a non-linear relationship. It's really inverted U-shaped. So what appears to be going on is that as we increase the amount of purifier, the yield initially improves, but then at some point we put too much of this purifier in and it actually hinders us. So the yield drops beyond a certain point. So the upshot is we've got the wrong model. We need to find the right model, and then that will tell us how much purifier to put in. So I'm going to add a quadratic term to this. So before I do that, if I do an A-B line on fit, you're going to see how dreadful that linear fit is. So let's have a new model, fit2, and fit2 is going to be a regression of y on x plus, now to get a quadratic term, I'm going to put in I at x squared. Now this I function protects what's inside of it. Now normally R is going to interpret x caret 2 as being an interaction of x with itself, and that's not what we want. We want a quadratic term, and that's why we have to stick the I around it. If you do a help on formula, so question mark formula, you can get some help on that. So if you do question mark formula, my M key is starting to stick. So if we go get some help, you can read all about this I function on that help page. All right, good. Let's now do a summary on fit2. So here's what you get with fit2. Let's begin by testing the overall significance of the model. So if we test the null hypothesis that neither the x nor the x squared term affect y, in other words, the linear slope and the quadratic slope are both equal to 0, well, we can reject that null hypothesis. It's very highly significant, and we conclude that there really is a relationship here. It's just not linear. And so we look upstairs, and here's the exact equation. So we have our equation up here, and both these terms are significant. Now if I want to see the fitted function, there's a number of ways I can do this. I'm going to first generate a bunch of x's. So if you look at my plot, x's range from 0 to 10. So let's have a sequence of x values from 0 to 10 by equals 0.1. So this is what I just did. I generated x values from 0 to 10. Now if I do a lines command, I'm going to use x, this x thing I just created for the x values. And one way to get the estimated regression model is to simply type the equation. Now this is not a great way, but I think it makes it very concrete. So let's do that. So what is the estimated regression equation? It's 7.1664. I'm getting that from up here. Okay. Plus, I could copy this down if you'd like. So I'll just do a copy, paste, and I have to multiply that by x. And then let's see. We have another term which is negative 0.96. I'll just copy that, and we'll paste it, and that has to get multiplied by x squared. So if I hit enter, you're going to see I've got a pretty nice fit. Now a slightly better way would have been to do something like this. So let's do lines x, and then I'm going to take predict, and we're going to use fit2 and a data frame. I'm going to have a variable x in that data frame that equals x, which is that sequence from 0 to 10. And just to distinguish this from the other one, why don't I give this a color of 2, which makes it red. And so you notice you get essentially the same curve without the rounding error. So up here I was only using about 5 or 6 accurate digits. With this fitted object, I'm getting something more like 15 or 16 accurate digits. Another question that we might have is, what is the optimal amount of purifier that I should put in? So if you go look at the curve, you can just about eyeball it, and it's about 6-ish is what I should be putting in. But according to the course packet, if you go back to the course packet, we should be able to take minus the linear effect over 2 times the quadratic effect and get a more precise value. So I'm just going to say B is the coefficients of fit 2. So here are those coefficients that we have. So we're going to take minus the linear coefficient. So if you take minus B2, check to make sure we got that right. We sure did. So if we take minus the linear coefficient, divide by 2 times the quadratic coefficient, we see that we get about 6, something a little bit bigger than 6. And the plot, our inspection of the plot led us to about the right answer. We said about 6, and it's slightly more than 6. So we would optimize or maximize our yield if we put about 6.08 units of purifier in.